This video is going to be about the difference between an explicit function and an implicit function. More like explicit ones are ones that you're probably familiar with, like y equals x squared plus 3, or y equals the square root of x plus 3 minus 9, or something like anything that has y equals everything else that doesn't have a y in it. And whenever you have a function where you can't solve for y, like on these, maybe like y squared plus 3x equals 9 minus 2y, this function is an implicit function because there are more than one y that have different powers. It's too hard to solve for y, and in some cases impossible to solve for y. And so we call this an implicit form. We call this explicitly defined functions. So maybe like sine of x plus y equals 3x minus y, or something like that. These are implicit over here. Ones that you can't say y equals everything else. So here's an example of an implicit function where if I wanted to know the derivative of this function, all I would have to do is take the derivative of all these pieces with respect to x. The only thing is, when you're differentiating y with respect to x, the letters don't match up. So if I wanted to differentiate x squared with respect to x, that's what we've been doing the whole time in calculus, and that would just be 2x, because you're taking the derivative of an x with respect to x. But when the letters don't match up, if I wanted to take the derivative of, let's say, y squared, like right here, it's not as easy. These letters don't match up, so you have to apply the chain rule, which is to bring the 2 down, rewrite the y, take 1 off the power, times the derivative of the inside, or the peanut as we called it, which is dy dx, the derivative of y with respect to x. We don't really know what that is, so this is the way to write the dy dx. This is the way to write derivative of y with respect to x. So over here, if I took the derivative of each side, taking the derivative of the left side would give me 2y dy dx plus the derivative of 2x with respect to x. We can just differentiate as normal, so this would be a 2, equals the derivative of 6y with respect to x. So again, I have to use a 6 dy dx because of the fact that this is a y. The derivative of y with respect to x is just dy dx. Then you want to get dy dx. We want this to say dy dx equals whatever it equals. So we're going to move this over here and move the 2 to the other side. So subtract 6 dy dx from each side. And now we want to isolate the dy dx on this side. And so what we're going to do is factor out a dy dx. So we have 2y minus 6 left over equals negative 2. And then we can divide each side by 2y minus 6, and there you have it, dy dx. So this means I need to know a y coordinate to know the derivative of this equation. And so all you need to do, take the derivative of each side with respect to x. Sometimes you have to apply the chain rule. Isolate the dy dx on one side, get everything else on the other side. And when you're finished, it will look like this. Dy dx equals everything that doesn't have a dy dx in it. So here's another example of an implicitly defined equation where we can't really say y equals everything. So we'll call this implicit, which means we need to use implicit differentiation if we want to find dy dx, which is another way to say y prime, by the way. So this derivative of x cubed with respect to x is just 3x squared. We can differentiate that as normal. Minus, okay, now I have a product right here. So I have 2 terms. And differentiating this product will involve the product rule. First term, just rewrite the first term times the derivative of the second term. Derivative of y with respect to x is just dy dx. Plus, rewrite the second term, take the derivative of the first term, derivative of x with respect to x is 1. And plus, y squared, derivative of y squared with respect to x is bring the 2 down, rewrite the y, take 1 off the power, which is invisible 1, times dy dx. The derivative of the peanut, or the derivative of the inside, equals the derivative of 4 with respect to x is 0. Now we need to clean all this up, so probably distribute this negative. Okay, and we're just still trying to solve for dy dx, which means we still need to get dy dx equals everything else. So we want to keep everything with the dy dx, like this term, and this term. So all of this and all of this need to stay on the left. These other two need to go over to the right side. So we have negative x dy dx plus 2y dy dx equals, bring the y over here, so it'll be a y, bring the 3x squared over here, minus 3x squared. So all I did was kept these two on the left side, put these two on the right side. Then factor out the dy dx. So write down what's left over. If I take the dy dx out of here, I have negative x. Take it out of this one, plus 2y equals y minus 3x squared. You'll notice that dy dx is by itself if I divide each side by what's left right here. So these will cancel. So y minus 3x squared over negative x plus 2y is what the derivative is for that function. Now, you'll notice that this derivative has x's and y's in it. That means that in order to find the derivative, you need the whole ordered pair, the x and the y, not like in the beginning of the chapter where in an explicit function, if you take the derivative is in terms of only x, so you only need to plug in the x coordinate. Here you need the rest of the ordered pair. So if I gave you a function like this one, and I said at the ordered pair 0, 2 or something like that, you'd have to come down here and put a 0 in for x and a 2 in for y. So that would be 2 minus 0, which is a 2, and 0 plus 4, so the derivative is 1/2. And if maybe I said what is the equation of the tangent line at that ordered pair, you'd have to say, here's my point, here's my slope, y minus y equals m times x minus x. So this would be an equation of the tangent line. So if all I ask for is what is the slope of the tangent line, that's this. If I asked you solve for dy dx, that was the green part. Maybe write an equation, you'd have to come back and use the formula for the equation. This happens to be point slope form. And that's all for implicit differentiation. So the next video will be about how to find the second derivative with implicit differentiation.